For our second lecture in the dynamics unit, we're going to jump to section 3.1 of the textbook, and we're going to cover frames of reference. Now, imagine that you're at an air show, and you see some airplanes that are flying in formation. This picture here shows, I believe these are Canadian Snowbird aircraft. And these planes are moving in formation. If you're observing them from the ground, it appears that they would be moving at a very high velocity. But if you observe the plane, one plane, from the frame of reference of another plane in the formation, the plane would have zero velocity in that frame of reference. So an observer on the ground sees the plane's moving in formation very fast. An observer in one plane sees the other planes moving at because they're moving at the same speed as them, they would see them as if they were moving at zero velocity. So in physics, no frame of reference is given preference over any other. So in the frame of reference of the observers on the ground, the planes move relative to the ground. But in the frame of reference of each pilot, the planes do not move with respect to each other. So I'd like you to copy down the definition of frame of reference here. You may want to pause to do that. But a frame of reference is a coordinate system relative to which motion is described or observed. So a question you might ask is, how can you tell if two objects are moving in motion with respect to each other? And one way to do that is to compare a straight line segment that connects these two objects. So let's imagine there's an object 1 and we have an object 2. If object 1 is traveling down at a velocity of, we'll say v1 equals 10 meters per second, and object 2 is traveling down at a v2 of 20 meters per second. The straight line segment of them after 1 second, or at when time equals 0, rather, would be this distance here, and we'll just call that distance d. Now, if after 1 second we observe these two, object 1 has traveled down 10 meters, object 2 has traveled 20 meters, but the distance vertically from object 2 to the plane where object 1 was is now 10 meters, and the distance between them is still that distance d. However, the distance connecting the two is now larger than d. It's actually the square root of d squared plus 10 squared. So because this straight line distance changed from d to the square root of d squared plus 10 squared, we can say that object 1 is moving with respect to object 2. WRT is a short form for with respect to. This is an example of when the straight line segment changes in length. Another quick example, if we have object 1 and object 2, and they are both moving at the same velocity, 5 meters per second, for example. In the second diagram, the distance between them, d, would not change. So, in this case, object 1 is not moving with respect to object 2. Now we could have another situation where the direction of the line segment between them changes. So in this case, we've been kind of considering the direction to be from 1 to 2, from 1 to 2, 1 to 2, and 1 to 2. If we have a situation where object 1 in our initial state and object 2 have a straight line segment of d after a specific time, and then the second time segment they've swapped places, we can say that object 1 moves with respect to object 2. So anytime we can see the straight line segment between two objects change in length or direction, or both of these, we can say that the objects are moving with respect to each other. So is there a right or wrong way to choose a frame of reference? There is no right or wrong way to choose a frame of reference, but what we do in physics is we typically choose the frame of reference that would make our calculations the easiest. This is a skill you'll learn as you go further on in this course, but I'll try to give you some notes and tips as these lectures go on. So now let's imagine you're driving in a car, or you're riding in a car rather. So when a car is moving at constant velocity, motion inside the car is similar to motion in a non-moving car. So if you're a passenger inside of the car that is traveling at a constant velocity, if you throw a ball directly up in the air, the ball will fall directly back down to your hand. This is because the acceleration is equal to 0, and that means that the frame of reference is an inertial frame of reference. But if the car accelerates or decelerates while the ball is in the air, the ball will either fly forwards or backwards. This is because when we have an acceleration that's not equal to 0, the frame of reference changes from inertial to non-inertial. So if the car accelerates, the frame of reference is no longer inertial. It's now non-inertial, and Newton's laws would not apply. But in a frame of reference that is inertial, Newton's laws do apply. So I'd like you to copy down this definition for inertial frame of reference. It occurs when the acceleration is equal to 0, and we know that Newton's laws are valid in an inertial frame of reference. Then I'd like you to copy down this definition for a non-inertial frame of reference. This is when the acceleration is not equal to 0. When we have a frame of reference that is accelerating, Newton's laws are no longer valid. So one thing to note as well, if you're moving in a car, or if you're in a vehicle or some sort of object that's moving at a constant velocity, if the car or vehicle had no windows and there were no bumps on the road, there was no other vibrations caused by the vehicle, there's no way to see what's happening outside. If that were the case, there would be no experiments you can conduct that would allow you to determine whether the car was moving or at rest. This is going to be very crucial when we look at relativity and other aspects of this course in the future. So another example, another thing to look at with inertial and non-inertial frames of reference in a car, let's look at this passenger here. And this person's in a car, they have a seatbelt. These are 3 moments in time showing this person in the car. And because the acceleration is 0, the person is not moving. And one way we can tell that the person is not moving is that the dot on their shoulder and the X that is on the, not the headrest, but I guess the top of the seat, that straight line distance between the two has not changed. It's remained constant throughout. But once the car decelerates, we now hit we're now in a non-inertial frame of reference, and the person moves forward. The seatbelt kind of pulls them back. But what you'll notice is during the first 3 frames, the first 3 time periods, the person is not in an inertial state. The straight line segment is not changing in direction or length. But during the non-inertial frames, the straight line segment has increased. This means that we can say that the car is accelerating, or in this case, decelerating, an acceleration that is negative. So this slide is a very nice concept organizer to help you determine whether you can use Newton's laws of motion or not. So those 5 laws that or those 5 equations that we use are also considered with Newton's laws. And what we basically do with this concept organizer is we first determine what the frame of reference we're looking at is, and we determine if the acceleration within the frame of reference is 0. If it's not, then we have a changing velocity, which means we have a non-inertial frame of reference and Newton's laws do not apply. If it is, then we have to look at whether it's at rest or it has a constant velocity, and then we can decide, or then we know that, or rather we would know, because the acceleration is 0, that we're in an inertial frame of reference and we can use Newton's laws. So in most cases, it's easier to work in an inertial frame of reference because you can use Newton's laws of motion. But a lot of times we have situations where there isn't exactly a non-inertial frame of reference in a specific situation. So what some physicists do is they create fictitious forces that represent inertial effects. We perceive these as forces to make a non-inertial frame of reference into an inertial frame of reference. This would make the math easier. So fictitious forces, this is something I'd like you to copy down. They are inertial forces that are perceived as a force in a non-inertial frame of reference. They do not exist, but we use them to create an inertial frame of reference. And within the inertial frame of reference, you could argue that they do exist because they represent those forces that would turn it into a non-inertial frame of reference. But in reality, they're not actual forces. So here's an example. If we have a merry-go-round, merry-go-round spins, and it feels as if you're being pushed to the outside of the merry-go-round circle. This force in a rotating frame of reference, acting away from the center, is a fictitious force that we call the centrifugal force. Now, one application of the centrifugal force is in the use of centrifuges. And in medical laboratories, centrifuges are used to separate blood samples. So the blood samples are spun at a very high velocity, and what happens is the denser materials in the blood move towards the bottom of the tube. And the denser materials in blood are usually red blood cells. The red blood cells would settle at the bottom, and the less dense material would settle at the top. This would help separate the blood samples so that a lab technician or a medical practitioner can do what they need with those samples of the blood. They can take the components that they exactly need. So there's going to be a few questions you have on elevators in this course. Elevators are a nice application of physics that allows us to kind of observe a frame of reference and a non-inertial frame of reference and what the effect of them are quite easily, because there's something we are familiar with. So passengers in a high-speed elevator, they feel as though they are being pressed heavily against the floor when the elevator starts moving up. And after the elevator reaches its maximum speed, the feeling disappears. So the question here is, what do the elevator and passengers form? When do the elevator and passengers form an inertial frame of reference? And when do they form a non-inertial frame of reference? So when the elevator itself is at rest or at a constant velocity, we have an inertial frame of reference. The passenger wouldn't feel any feeling of being kind of compressed or pushed in any direction. But while the elevator is accelerating, the passenger would feel that they're being pressed because we're in a non-inertial frame of reference. Another question, before the elevator starts moving, what forces are acting on the passengers? And how large is the external unbalanced force? So remember, if you remember from last year, grade 11, the external unbalanced force means that we would have, using our F equals ma equation, we would have an acceleration. So before the elevator starts moving, the forces are the force of gravity and the normal force. They have a net force of 0. That means that our acceleration is 0 because F equals ma would have to be, the a would have to be 0 in order to make the F net 0. So for a person standing outside the elevator, are they in an inertial or a non-inertial frame of reference? And the question for this is a bit more complicated. So it says here that Earth and everything on it are in a continual circular motion. So Earth is rotating on its axis, traveling around the sun, and circling the center of the galaxy. The direction of motion is constantly changing, which means the motion is accelerated. So Earth is a non-inertial frame of reference. However, in everyday life, the effects of Earth's rotation are usually not detectable. So we can really look at this from the larger picture of your person sitting on the Earth, and the Earth is both rotating around the sun, rotating along its axis, and tilting along its axis, while the sun rotates around the Milky Way, which is also moving away from the center of the galaxy. So we have all this different motion that's happening, but really we just consider it an inertial frame of reference because these effects, we don't notice them. We're all moving together at the same on the same Earth, so we don't notice those effects. So is that pressure the passengers feel a fictitious force? So it's an inertial effect. It's an effect of the body wanting to stay at rest. So this is Newton's first law. A body at rest tends to stay at rest. A body in motion tends to stay in motion. So it's that inertial effect that causes that. It's not a real force. So let's look back at this is a situation where you're on a train and another train on a parallel track is moving at the same velocity. If you see a passenger in the other train throwing a ball vertically up in the air, you would see the ball as going up and down directly. If you're both traveling, the trains are both traveling at the same velocity and they're parallel to each other, and you're looking directly at this person, they would throw that ball up, it would fall directly back down. But if the trains were moving in opposite directions, the ball would actually have a parabolic motion. It would almost be as if you were somebody outside the train was throwing the ball and you were along the horizontal axis and you were observing it rise and fall.